Oceans cover roughly 70% of the Earth's surface. Yet our understanding of what goes on beneath the waves is tiny.
Well, I've often heard it said that we know more about the surface of the moon than we do about our own oceans. They represent probably the greatest portion of the unexplored parts of our planet because of how difficult it is to get there.
However, one group of engineers, led by explorer Victor Vescovo, are determined to change this by attempting the impossible.
When Victor approached us in 2015, the only thing he knew he wanted to do was he wanted to dive to the deepest point in each of the 5 oceans, which is something that nobody had ever done before.
To achieve this monumental goal, the team have created a vehicle like no other on planet Earth. This is the Triton 36002. Or, as she's known to her crew, the limiting factor.
Well, this is the deepest diving certified submersible in the world right now. And she's our baby. We basically built this thing from concept to where it is now, and it's done some amazing diving.
The limiting factor is probably the most intricate undersea vessel taken on in history.
It is entirely unique in the world. There is no other craft like it, before or since.
This groundbreaking vessel's list of accomplishments already include reaching the bottom of each of the 5 oceans, as well as more than 10 dives to the deepest place on planet Earth, Challenger Deep.
Surface LF, depth 10884, heading 180, life support good.
It's made some remarkable scientific achievements. It's collected 400,000 samples, identified 40 new species, mapped 750,000 square kilometers of ocean. So the contributions to science have been significant as well. I often use the word revolutionary because I think it's apt. I think it absolutely describes that sub and the importance of it in our oceanic journey.
This game-changing submersible is built to explore the ultra-deep. Carried to location by its own dedicated support vessel, the Pressure Drop. Once at the dive site, it's raised into position and lowered into the water before descending to depths of almost 11,000 meters. On board, 10 thrusters allow for movement in all directions. Whilst inside the pressure vessel, a dedicated life support system allows a 2-person crew to spend up to 16 hours underwater. All this engineering combined means the sub can reach depths greater than the height of the world's tallest building, stacked end-to-end 13 times. Today, off the coast of Hawaii, the team are taking this trailblazing vessel on a training dive.
My hatch is secure, life support running. We are good for launch.
Inside, Triton's submarine co-founder Patrick Leahy is teaching crewmate Tim McDonald as he prepares to join the small group of people qualified to pilot this one-of-a-kind machine.
Sub away, I'm going to go ahead and secure thrusters.
Roger that. All lines are clear. Swimmer is clear. You are clear to dive, cleared to dive.
Buddy, go have some fun, man. Good luck, Tim.
Give it a whirl with the thrusters. Nice down thrust. Should go under any second now. There you go. Come on.
Go.
Keep going. Don't let off on it.
The team have constructed a record-breaking piece of engineering. But how have they made this submersible capable of descending almost 11 kilometers beneath the waves?
I would say that, without question, the deepest parts of our ocean are the most formidable parts of our planet to visit.
Where the colossal water pressure can crush all but the strongest man-made materials.
We need to be 100% on our engineering, on our designing, and our tolerances. They have to be 100%. We just don't have room for error.
And how can they ensure that, should an emergency occur, they can get the crew back to the surface in one piece?
We cannot afford to make any mistakes. People's lives depend on it.
Getting to the deepest parts of the ocean requires engineers to radically rethink every aspect of submersible design. This is the Deep Submergence Support Vehicle Pressure Drop, and the record-breaking submarine, the limiting factor. Inside the two-person pressure vessel, pilot and passenger are able to navigate their surroundings thanks to 10 electrically powered thrusters that offer control in all directions, whilst 3 acrylic viewports and 10 lights designed to replicate the color temperature of the world above offer a window into the abyss. This record-breaking vessel is allowing humans to explore parts of the ocean few have ever seen. But getting to this point has required Patrick and the team to overcome some colossal engineering challenges.
Connecting people viscerally with their environment, allowing them to experience the deep ocean in real time, is powerful stuff. It is exciting, it is memorable. The disadvantage is the human component adds complexity, and we have to work harder to develop something that we know human beings are going to get into because we want them to come back safely. Unfortunately, you can't just take a sub that's rated to 500 meters or 1,000 meters, or even a sub that's designed to dive to 6,000 meters, because the pressures are much higher. There's nothing that you can buy off the shelf. There's just not a row in Home Depot where you can go to buy full ocean depth parts for a submarine.
To find a solution, the team must turn to the great underwater exploration pioneers of the past. For centuries, man has been obsessed with what's occurring under the ocean. But for a long time, the deepest you could dive was dictated by how long you could hold your breath. In the 1820s, brothers Charles and John Dean designed an underwater breathing helmet to overcome this problem, which worked great, up to a point. By the 1930s, explorers were making it to depths of almost 1,000 meters. William Beebe and Otis Barton reached a record 923 meters deep in their bathysphere, and they could have gone further if they hadn't run out of rope. Former submariner Craig Karsh has come to the National Museum of the United States Navy in Washington, D.C. to discover a vessel that redefined underwater exploration.
Wow, this is really an amazing piece of equipment.
This is the Trieste.
Wow, this is a lot bigger than I expected. You can see that it looks a lot like a modern nuclear submarine as far as a metal tube, but here you have this gondola where the crew would have sat.
Constructed in the 1950s, its mission was simple: transport a two-man crew to the bottom of the deepest part of the ocean for the very first time in history.
Before the Trieste, the record was about 1,000 meters for how deep a vessel had gone, and the Navy wanted to go to 10,000 meters. So it required just a fantastic amount of engineering to get there.
The Trieste was designed and built by Swiss physicist and adventurer Auguste Piccard. On the 23rd of January 1960, his son Jacques and US Navy Lieutenant Don Walsh climbed aboard in preparation for their first attempt at a record-breaking dive.
You can see the ladder that the crew would have climbed down. There would have been tremendous anticipation. You're climbing into a very dark steel chamber, and once you shut that door, everything around you needs to work, because once you get down that far, there is no one coming to rescue you.
At the very bottom of the Mariana Trench, the gondola with the 2 men inside would be experiencing over a ton of pressure per square centimetre acting upon it.
This gondola, the steel, is 5 inches thick to hold back that pressure. Definitely the most dramatic thing is this window with only that 2-inch opening to look out of. There was really a lot of innovation that went into this. They had to develop a special polycarbonate that would withstand the tremendous pressure, because any crack that allowed water to enter would just become the most powerful pressure washer jet that you can imagine.
But not only did the crushing pressure present an enormous danger to the crew, it also meant that using a traditional air and water ballasting system wasn't an option. To demonstrate, Craig has prepared an experiment.
When a traditional submarine wants to sink, they fill their ballast tanks with water. They flood them, letting the air out, and the submarine would then lose that positive buoyancy, become negatively buoyant, and be allowed to sink. When it comes time that you need to add positive buoyancy and come back to the surface, you would use compressed air to force that water out of the ballast tank, and the submarine would rise. In the Trieste case, going to a depth of 10,000 meters, the air wouldn't have worked. The pressures are just too great. So Picard came up with an ingenious solution of using a petroleum gasoline-like product that's about 30% lighter than water. So as you can see, despite being totally full, it is positively buoyant. So now to simulate the gondola underneath the main body of the Trieste, you can see that it's still enough positive buoyancy that it continues to float on the surface. So they had a precisely measured system of ballast that they added, which would allow the vessel to sink to the bottom. They had a system to release this ballast, and up the Trieste went back to the surface.
On board the Trieste, 2 ballast tanks containing roughly 9 tons of iron pellets allowed the crew to adjust their buoyancy throughout the dive.
Here you can see these big ballast tanks. There's this one up in the front and there's one in the back. Once they reached the bottom, the mission was over, it was time to come up. They had a system of controls through these wires that they could open this to allow the shot to come out, removing weight from the submersible, and the Trieste would have been able to slowly rise.
After descending for almost 5 hours, Picard and Walsh reached a depth of 10,912 meters, becoming the first humans to ever reach the deepest part of the Earth's oceans.
The Trieste truly is incredible. To go down to 10,000 meters, shattering prior records by a factor of 10. It's really hard to understate the magnitude of the accomplishment of what these pioneers did.
Today, the team have taken the engineering at the core of the Trieste and developed it for modern underwater exploration.
Surface, LF, depth 700 meters, life support good, over.
CO2 is nice, hull's starting to cool.
Deep beneath the Pacific Ocean, on their training dive, Patrick and Tim are slowly descending to their target depth of just over 1,500 meters.
We'll just go down till we get maybe to 1,300 meters and we start to pick up bottom with the altimeter and then come down nice and slow.
More than half a century since the Trieste, the 36,002 has capabilities that Picard and the team could have only dreamt of.
I think that you have to tip your hat to the vehicles that preceded this one, the Trieste being a great example. But we have capabilities that were completely unheard of 60 years ago, let alone 10 years ago. And we weren't interested in building a sub that was just an elevator to the bottom and back up again. We had to build a vehicle that was capable of conducting actual meaningful work on the bottom.
It's this guiding principle that's driven Patrick and the team to create a submersible that is far more capable than anything that preceded it.
One of the things you'll notice when you look at the submarine right away is it's very tall. And the reason it's like that is because the submarine has to transit vertically through the water column a great distance, as much as 7 miles. It's a long way, and so we want to have the vehicle run very efficiently in the vertical direction, both when it's diving and when it's returning back to the surface. And then if you come to the front, you'll notice there are 3 viewports. That's where the pilot and the passenger can look out. There's a manipulator arm, which is the device that's used to interact with the environment. If you want to collect samples, if you want to recover something. It also has lighting and camera systems because, of course, when you get to great depth, one of the things is a complete absence of light.
60 years on from the Trieste, engineers have also managed to design a modern solution to the deep water buoyancy problem faced by Picard.
The way this vehicle differs from the Trieste is we don't have to use gasoline for buoyancy. We have this wonderful material called syntactic foam.
Strong enough to be unaffected by the pressure, the syntactic foam modules on the 36002 are a lightweight solution to the buoyancy problem.
It's a strong material. It can be cut and shaped to create the complex structural shape that this vehicle has that allows it to travel through the water column very quickly.
On the surface, the 36002 is kept positively buoyant thanks to 7,500 litres of syntactic foam and 2 air-filled ballast tanks. To descend, the tanks are flooded and the descent begins. As they approach the bottom, the pilot releases steel weights, balancing the vessel's buoyancy until it floats just above the ocean floor. When it's time to ascend, the remaining steel is dropped, and the submarine returns to the surface. It's a cutting-edge material that helps the pilot to accurately control their position in some of the most perilous places on Earth.
We do the same thing we talked about, setting up your ballast.
Yep.
So you're 50 meters off, because this is unknown terrain, just to avoid the possibility you end up crashing it. Because, I mean, I've seen boulders, that are 50, 100 feet tall.
I think we just need to be super cautious and see our altitude.
Syntactic foam has contributed to making this one of the most remarkable vehicles that has ever been conceived.
The deepest parts of our ocean are some of the least explored places on our planet. But now, humankind has a radically new machine that looks set to change things. This is the Triton 36002. Designed to venture to the most inhospitable underwater locations on Earth, it's a game-changing feat of engineering. Capable of transporting 2 people to a depth of almost 11,000 meters. Protecting the occupants from the crushing force outside is a 90mm thick pressure vessel that must withstand the equivalent weight of 291 jumbo jets pressing down on it. Having been involved with the design of the pressure vessel from point of concept, Patrick Leahy knows this cutting-edge cockpit better than most.
Welcome to the limiting factor interior. You can see the pressure hull. There's a bank of oxygen bottles that are above here. Over here we have ballast control and life support panel, and this is the control joystick. This is the interface between the pilot and the propulsion system. So the limiting factor is most similar to a helicopter in the way that it operates. You know, like a helicopter, the submarine can hover, it can go forwards and backwards and up and down. It's a wonderful way to explore the ocean. It's really sublime, it's straightforward, and very comfortable.
It may be comfortable on the inside, but on the outside, it's having to deal with a colossal amount of pressure.
So as you dive deeper, you know, the pressure increases. Full ocean depth, we're at about 15,000 psi per square inch on the vessel.
The task of maintaining this critical component falls to industrial designer Kelvin McGee.
So the best shape for the pressure vessel is a perfect brown ball. So it's got equal pressure exerting on all sides at all times. It has to be very precise. If you deviate from that, it creates a pressure spot and could be prone to collapsing. So it has to be absolute perfect.
But getting it right is an enormous challenge.
Boy, turning chunks of metal into a perfect sphere is very difficult. It was like 0.1% of a millimeter that it had to be within that tolerance. If we had a weakness or a design flaw in the metal, it's prone to failure, and failure is just not an option.
To create the perfect metal sphere, the team must draw inspiration from an innovation born in the Industrial Revolution. In the suburbs of Cleveland in the USA.
So, we're heating up some bars of steel here to about 1,000 degrees C. This will make the metal a lot more malleable, easy to work with.
Mechanical engineer Jennifer Kadlewick is discovering the secrets behind a profession that dates back millennia.
The heat changes the structure so that I can simply strike it with a hammer and bend it right into shape. But this process is fine when you're making small parts in small numbers, but during the Industrial Revolution, when there was a high demand for much larger parts, doing things by hand like this just wasn't going to work.
Fortunately, one man was working on a solution. In 1795, British engineer Joseph Bramah patented a new type of press, one that replaced muscle power with hydraulic pressure, allowing machines to apply more force than ever before. And at the Howmet Aerospace plant,
Wow, I can't believe I'm actually inside of here. It's absolutely amazing.
Jennifer is witnessing Bramah's invention brought to life on an epic scale. This is a 3,000-ton hydraulic press.
Oh, I can feel the heat coming off that metal.
Used to create giant metal parts for the aviation industry. It's based on Bramah's original design.
Just like at the blacksmith, the ingot is heated up, it's compressed with the machine instead of hitting it with a hammer.
At full power, this press can apply a force equivalent to the weight of 3 Boeing 747 jets, shaping and flattening giant pieces of aluminium with ease.
It's absolutely incredible to see it happening. It's like squashing a piece of foam by hand. And even though it's been well over 100 years since Bramah first patented the idea, the hydraulic press and system still works the same today.
To demonstrate the engineering behind it, Jennifer has prepared an experiment.
All right, so here we have a scale model of the hydraulic press. We have small cylinders that pump fluid to a larger cylinder. And in doing this, the fluid can't be compressed like a gas. It'll just take all the load and the pressure and transfer it from the small cylinder to the large cylinder. The one disadvantage, though, that I have is you'll see how many times that I have to move this cylinder in order to compress it, but I can easily squish this orange flat. So this is what we call mechanical advantage.
On the 3,000-ton press, this mechanical advantage is created in the same way. But instead of building up the pressure by hand, fluid is passed between 2 sets of electrically powered pumps.
So here we are in the pump room. As you can see, there's some smaller pumps in the back that fill up the larger pumps, and that's what allows us to create the enormous amount of force when you close a forging press. Each one carries an equal amount of load. We have 3 large pumps, so about a ton each.
The hydraulic press is an invention which has revolutionized manufacturing. And by increasing the size of the components, Brahma's design can be scaled up to create a machine of astronomical proportions.
This is absolutely astounding. It is totally huge, this press. Wow, that's hot. This is the 50,000-ton press. This is over 15 times the one we just saw, which was 3,000 tons.
Standing almost 30 meters high and weighing 300 tons, the plant's 50,000-ton press is one of the largest on the planet.
Now, if you think of an automobile that's about a ton, and you were to stack them one on top of the other, you could have a stack that's 36 miles tall to create the equivalent amount of force or pressure that this machine exerts.
Centuries after the idea was first conceived, the hydraulic press continues to shape the world around us.
Brahma's invention is really a foundation in the Industrial Revolution. It allowed us to form large metal parts using machines rather than manpower. And this is really the basis for hydraulic systems today.
More than 1,500 meters beneath the Pacific Ocean, Patrick and Tim are at the midpoint of their training dive.
Just very slowly, because this thing is massively more powerful than you give it credit for.
Protecting them from the crushing pressure outside is a metal sphere constructed with a hydraulic press, based on Brahma's revolutionary design.
So now what we're going to do is we're just going to make a nice, careful approach. Yeah, there's the bottom.
Surface LF, depth 1545, heading 100, life support good, over.
See how she's very controllable.
Yeah, super quick.
Oh, see the eel?
Yeah.
You just zipped by the front.
Yeah, it was over this way before.
Having been involved with the project since the outset, industrial designer Kelvin McGee watched this vital component take shape.
So this is the pressure vessel, and it actually sits quite low in the submersible. And this is what keeps everybody healthy and happy as they dive down. And yeah, it's our little baby. It started its life as a flat piece of titanium.
At this forging plant in Wisconsin, 2 giant titanium ingots that will each go on to form the 2 halves of the pressure vessel are heated to over 500 degrees Celsius to make them malleable.
We constructed it from titanium because it's a very, very strong material, and it'll hold the pressure quite comfortably at the depths that we were going to. We could have made it out of steel, but it would have made it so much heavier. The submersible would have been so much bigger.
To create the spherical form the team are looking for, a 15,000-ton hydraulic press is fitted with a specially designed die.
Once the ingot's loaded into it, the hydraulic press came down. When it pressed down onto the ingot, it actually formed around that dome. And then we started the initial forming of each hemisphere. It's an amazing thing to see. There's flames, there's smoke, there's steam. And to see how that thick piece of titanium is, within minutes formed into what was the start of the submersible, it was absolutely incredible to see.
Once cool, the 2 hemispheres are machined by a computer-guided lathe to an accuracy of within 99.933% of true spherical form.
I think it was like 1% of 1 millimeter. That had to be perfectly precise.
Once complete, the team faced the challenge of working out how to join the 2 hemispheres together without creating a weak point that could potentially rupture as the vessel dives.
It's actually bolted together because when you start welding on metals, it actually changes the structure of the metal. It can become more brittle. And then, yeah, you're down deep until you find that flaw. You can't see it. There's 24 bolts around this that hold it into place. And each one of them is a titanium bolt and a titanium bracket that actually bolts onto each hemisphere. And then they're bolted together. So it's a metal-to-metal seal. And this is why the machining has to be so perfect.
To put this to the test, the completed pressure vessel is flown to the Krylov State Research Center in St. Petersburg, Russia. At this unique facility, the team are able to test the hull to its target depth of 11,000 meters and beyond. Once unloaded, the pressure vessel is lowered deep inside the test chamber, which is then sealed tightly shut. Filled with water, and the pressure is gradually increased all the way up to the equivalent of being at almost 14,000 meters deep. 3,000 above the team's target.
Looking good, man.
Yeah, man.
Great. Have a submarine.
The engineering had to be checked and double-checked and triple-checked, and it had to be tested and tested and tested. The capability of this thing is just incredible.
The world of ocean science is being redefined by two game-changing vessels. The Triton 36,002 submarine and its support ship, the DSSV Pressure Drop. Combined, the pair are the ultimate tools for exploring the ultra-deep, allowing people to view life in one of the most unexplored parts of our planet. Deep in the Pacific Ocean, Patrick and Tim have completed their dive.
Surface, LF. We are requesting permission to drop surfacing weight.
And are now preparing to make their ascent.
Surfacing weight has been dropped. Freeboard weight has been released.
And then I recommend ditching the rest of your DBT weights. You only have 2 on each side, so.
By releasing the remaining dive weights, the vessel becomes positively buoyant and is free to slowly rise to the surface. But if for some reason the pilot was unable to carry out this process themselves, the team would need a way of making it happen automatically.
In the event that there is a full power loss at the bottom of the ocean, generally that would be a very big issue.
It's a situation electronics technician Shane Eigler must prepare for.
There is no chance of surface rescue as there is no vehicle capable of reaching the limiting factor on the bottom. So we had to engineer a way for the submersible to basically ascend itself under its own control without any interaction from the pilot.
To overcome this life or death problem, engineers must look to the innovations of the past for inspiration. Finding ways to escape a stricken submarine has posed a problem for engineers ever since their creation.
Oh no!
In the early 1900s, crews had to make do with breathing apparatus derived from the coal industry if they faced an emergency. During the 1930s, the US Navy developed the submarine rescue chamber. Attached to the trapped vessel's escape hatch, it created an airtight tunnel for submariners to climb through, before returning them to the surface. By the 1970s, specially designed rescue submarines arrived, which could hold up to 24 people and work up to a depth of 1,500 meters. But when diving almost 11 kilometers beneath the waves, you need something entirely different. Volunteer streetcar operator Eric Madison is at the National Capital Trolley Museum.
This is actually a lot of fun.
Discovering how an engineering innovation from the 1800s helped make city streets in Washington, D.C. a safer place to be.
Operating a streetcar on a city street, it's kind of challenging. You had to have really good senses and good eyes because you never knew when you had to make a sudden stop.
Streets packed with pedestrians, horses and cars all presented potential hazards that might require the operator to need to come to a stop in a split second. But in an emergency, streetcars like this one faced a problem with the stopping capability of their mechanical brakes.
Okay, hit the gong, release the brake, we're about to take off.
To demonstrate, Eric is heading down the track at full speed. Once in line with the green flag, he'll hit the brakes and see how far it takes to come to a stop.
Okay, so for a little frame of reference, 1101 is 44 feet long. So if you look down here to the green flag, where I began the braking application, to this point here, we've covered roughly about 2 car lengths. So it demonstrates that mechanical brakes would not be enough to stop this car in an emergency situation.
Luckily, a solution can be found in an unlikely innovation from the past. In 1825, English physicist and inventor William Sturgeon devised a method to improve the capability of a magnet. His invention relied on the principle of electromagnetism. When an electrical circuit is made, an almost imperceptible magnetic field is generated. Sturgeon discovered that by wrapping copper wire around an iron core, he could enhance and concentrate this field. And by switching the current on and off, he created the world's first electromagnet. Underneath car 1101, 4 high-power electromagnetic track brakes provide the perfect solution for emergency braking.
Here we are underneath the car, and the track brakes are mounted in between the wheels here. These coil springs hold the track brake up, so in normal operation you can see the track brake would just normally bounce along the top of the rail as the car is going down the street. When I apply the emergency brake, current comes through the back, energizes the track brake, and track brakes drop onto the top of the rail. So a normal braking application is about maybe 4 miles per hour per second, normal service brake, but with the electric track brake, that goes to about 9 miles per hour per second. So it's almost double the amount of braking effect.
To put the theory into practice, Eric is heading back out onto the track to repeat the experiment. This time, with the help of the electromagnetic brakes.
So I'm going to try to get the car up to as fast a speed as I can. Up to the switch, floor it. Passing line pole 50, and hit the track. All right, so you can see that from the green flag to where I stopped, it's about half a car length, so it's about half the length of where I stopped in the original brake test. So it really demonstrates just how important it is to have the electromagnetic track brake in an emergency situation.
Sturgeon's invention revolutionized the engineering world.
Today's modern streetcar and light rail vehicles still use the electromagnet for emergency stopping. But beyond transit, the electromagnet also has other uses, from MRI machines to cranes and computers, so it's hard to underestimate their impact in today's modern world.
Back on board in Hawaii, the team have taken Sturgeon's electromagnet and created a life-saving piece of engineering.
So what we have is 2 sets of roughly 40 kilogram weights, bar weights that go in here, and they are held onto the sub by this magnetic release system right here. So this is in the locked position. If the pilot does lose power to the submarine, the magnetic power is cut, that will release, weights will fall out of the bottom of the submarine. So the submarine will surface even without the pilot being able to control that.
As the submarine's syntactic foam keeps it positively buoyant at all times. By releasing the weights, the vessel is free to rise to the surface without the need for any electrical power.
To date, we have not had any issues that require the pilot to activate any systems in an emergency situation on the submarine. He has completed all dives of his own accord, come home on his own, everything intact, nothing released. The emergency systems on this vehicle are extreme, but they're there and hopefully we never have to use them.
After 2 hours underwater, the training dive is now complete. And Patrick and Tim are almost back at the surface.
Surface LF, depth 70 meters, heading 045.
Okay, so now what you need to do is get ready with your pumps and with your vertical thrusters. And then vertical up.
Roger that, clear to surface, surfacing now.
It's coming out. So now you can turn your verticals off.
We'll be with you in line.
Roger that, thank you very much.
It's a feat of engineering few thought possible.
I am extremely proud to be a part of this project, a once-in-a-lifetime opportunity that very few of us have got to experience, and very thankful and proud to be here.
By looking to great pioneers of the past for inspiration, adapting their ideas, refining their designs, and overcoming monumental challenges.
We put our heart and soul into this thing, and to watch it leave the surface and then to see it come back, it's an amazing feeling. It's my baby.
Engineers have constructed something radical.
As far as I'm concerned, the Triton 36,002, or the limiting factor, is by far one of the most significant oceanic creations ever.
And succeeded in making the impossible possible.
I am exceedingly proud to have been part of this project. It has been the privilege of my life. I don't know that I could top it.